Let's now switch to Caesar 2 to perform the analysis. So in Caesar 2 I'm going to create a new job file, I'll call it pipe, stored in my integration directory. This is a brand new file, so I'm using my custom units. And in the piping input I'm going to use the PCF input to construct the model. So I will choose the PCF file that we created in CADWorks, and the only thing I'm going to change here is the node numbering. I'm going to use the 2000 series node numbering and then hit begin processing. I'll now close the PCF import window. Now the import is complete and we can see the model. If I turn the node numbers on, we can see here is where the node numbering starts. Just turn the tooltips off at 2000. We step along the header all the way along to the vessel connection over here, and we then, if I skip next element, we then go along to the branch, where we start from the header and go towards the pump. As the analyst, I have options here. I can make changes. If, for example, I wish the flow of elements to go in the opposite direction, starting at the pump towards the header, I can set that. I can simply make a selection, right click, and, for example, invert the node numbering. So this now starts at the pump, and as I go next and cycle through the elements, we go towards the header. If I use the graphics, I can show, for example, the materials which have been imported from the CADWorks specification. A105 for the rigids, the valves, flanges. A106 grade B for the piping, and A234 WPB for the fittings. Opening the classic piping input, let's turn the legend off. I can see the temperature 250 degrees, the pressure, the hydrotest pressure, the fluid density, corrosion allowance, all the data that we set inside originally CADWorks P&ID. I'm going to turn off the reset view and finish off by changing the boundary conditions by adding anchors at both of the pump connections at 2290 on this one, and at the vessel connection like so. And now I'm ready to run the analysis. So in this example I'm just going to hit batch run the recommended set of load cases. Now that the analysis is complete, I can see load case 5 is red, failed the expansion stress check. Let's take a look at the results. Okay, I see that the highest stress is 205.7% of the allowable at 2300, 661 megapascals versus an allowable of 321. Reordering the report by ratio shows 2 red locations, 2 failures, 2 places where we're above 100%, 2010 and 2300. Using the graphics, viewing the 3D plot can assist with what's happening here. First of all, if I shade the model by stress level, I have anything below 40% is in white, above 60 is yellow, above 80 orange, above 100 red. And as we can see, the 2 red locations are those shown down here on the reducers at the pump connection. Not too surprising if we view the displaced shape of the system. Let's just exaggerate that. We can see, somewhat unsurprisingly, that this long leg is expanding. When the system gets hot, and much of that thermal expansion is being pushed over to this side around where the pumps are located, causing high bending and therefore high stresses around the pump location. So we have an overstress issue, and the issue is in our expansion load case. Typically, to resolve issues in the expansion case, adding flexibility would be a resolution. We can add additional flexibility without making a change to the model by including flexibility that's there in reality but just isn't included in our analysis model, such as adding further flexibility by connecting the steel frame to the restraints rather than using the rigid restraints that we have right now. To do that, we will export the steel frame from CADWorks to Caesar 2 for inclusion with our analysis. So let's close down the output and let's return to CADWorks to generate the Caesar 2 structural model. I'm going to remove the frame XREF from the piping model, and then in CADWorks structure I'm going to attach the piping in here. So I removed it from the previous drawing in order to avoid a circular reference. And the reason I'm doing this is in order to connect the piping and the steel inside Caesar 2, we need a node point where the pipe meets the steel. Of course, we have a node point in the piping, that's where the restraints are, but we need to add the node point in the structure. And the easiest way to do this is to add the node here inside CADWorks. So I'm going to do that by using the cut command, and I'm going to cut this member at the point where it's perpendicular to the pipe. And as you can see, this is now two separate members. I'll just repeat that function for the other three members where the U-bolt passes. So snap perpendicular each time. Making sure I pick the correct snap point. And the final fourth one, like so. So I can remove, detach the XREF here, and now I can export this frame to Caesar 2. To improve the export, I'm also going to change the grating to the simple representation. And I will now simply export, first of all, to Caesar 2, select the frame, and into my integration project directory, creating a native Caesar 2 structural file .str. Node numbering starting at 10, increments of 10 is OK. While I'm here in CADWorks structure, I will also export to GT_strudel for analysis later on. In the same folder, creating a native GT_strudel.gti file. Now let's return to Caesar 2, and I will open the steel frame. And then we jump to the Caesar 2 structural input module. Here we see our steel frame. There's the two section IDs, 8x28, 8x10. If I turn the node numbering on, and let's turn the reset view off, here I see the node numbers, and the only thing I need to do here is add the fixities at the base of the columns. Now, judging by the node numbers, this will be fairly easy. I have 50, 70, 90, 110, 130, so I can add a fix to here. That's all in steps of 20. We then go 130 to 160, so that's a step of 30. So 130 will be our last one on the first fixity. So I will fix between 50 and node 130, going in steps of 20, and I will all degrees of freedom will be fixed, like so. Next, I have 160 to 180, 200, 220, 40, 60, 80, 300, 320, 340, 60, 80, 400, all the way to 420. So I can actually fix from 160 to 420 in one go. So again, I'll add another fixer T from 160 to 420, the last node number to fix, going again in steps of 20, and again all degrees of freedom fixed. That leaves just a few more to do. We have 440, 60, 80, 500 we can fix in one go. So let's go to 440 to 500, again steps of 20, all fixed. Which leaves us with one remaining column that's not been fixed, node 20. So let's add one final fix and just fix node 20 on its own, fixed. And that's it, all the base of the column, all the columns are now fixed, so I will hit save. To save those changes, I can then combine the frame with the piping. The frame and the piping will be combined at the node numbers shown here, 5, 10, 20, 30 and 40. So I can close that and I can return to my piping input. So let's open and include the structural file, like so. And although these look like they're in the correct location, it just so happens that the origin is the same for the steel and the pipe. They're not actually connected. We now need to do that, which is done by adding a C node or a connecting node onto the restraints. So I'm going to add a C node here at 2190 to connect to 510. We must do it on both the Y restraint and the guide. Only the ones which have a C node defined, they're the only restraints that will have flexibilities assigned to. Fortunately, the graphics change colour of the restraint so we can easily see if we've missed one. So I'll just repeat for the remaining ones. And what we're doing here, well, actually the pipe centerline and the steel centerline are in the same location. Technically that's not correct. What we should really do is add a rigid construction element from the pipe centerline to the appropriate location on the steel and move the restraints down to the end of that construction element. However, for a 6-inch pipe, we're not going to introduce a huge amount of error here. So we will be okay. And I typed in the wrong node number there. Let's set these to 550, not 540. We can always check the node numbers if we wish. Sorry, that is 540. So I was correct the first time. A miscount there. These are 530. Like so. So now that I've got all the C nodes correct, I can once again run the analysis. Run the error checker, shows no issues around coordinate mismatches. So I'll again hit the batch run to run the analysis. Okay, the analysis is complete. Low case 5 is still shown in red. Let's take a look at the results. So it has reduced a little bit. We're down to now 194 megapascals, 621 instead of around 660. We've saved around 40 megapascals, maybe 10-15% in terms of stress. We were just failing quite spectacularly in the first place. So we need to do something further. So let's return back to the input and try another resolution. And we're going to try adding in an expansion loop. So when we add, let's hide the tooltips, when we added the expansion loop, the two questions we need to ask ourselves are, where will the loop be located and how big does the loop need to be? Well, I'm going to load the CADWorks model in the background so we can see our pipeline in context. So here I can see exactly what space I've got available by having the CAD model here in the background to give context. So this is quite a simple system. We've got quite a lot of space here. We're not too restricted on space. Of course, if this was a more complex system, clearly space would be at a premium, and being able to see exactly where our pipeline lies and see what space we've got makes this much easier and makes it possible for us to make a better decision as the analyst. How big does the loop need to be? Well, I'm going to ask Caesar 2 to figure that out for me by using the loop optimization wizard. Very straightforward to use. First of all, select the element I wish to design the loop on, which will be this one, which is 2170 to 2180. So let's pick that in the list, 2170 to 80. Pick the problem that we have that we want to resolve. Well, my problem is the expansion case, and it is a stress problem. And my maximum stress, my allowable is around 320 megapascals. Let's say I want the maximum stress to be no more than 250. The table then filters to display all the locations where the stress is above 250. And I'm going to say I don't want that stress to be 250 at a particular location. Rather, I want the max stress anywhere in the system to be no more than 250 megapascals. I will then add a flat loop in the center of the selected element, and I can now draw a cube of space to tell Caesar 2 how much room there is to insert the loop. Again, this is where having the CAD model can be very useful for restricting the size of the cube. We can stretch the cube, we can go vertically if we have vertical legs as well. I'll switch the view here so I've got a little bit more room to expand this cube. Something like that to avoid the steel frame. And once I'm happy, I hit design. Caesar 2 will then build the biggest loop it can within the space available, run the analysis in the background, and check the results compared to my target. And I see 116 here. So with the biggest loop in that space, we've hit 116 megapascals. That's below our target value, so we know we can achieve the target. Caesar 2 will then iterate to focus in on that target value, and the number in the converging row as we run through various iterations gets closer and closer to our target, in this case 250. After 6 iterations we've hit 250. Caesar 2 then tells me it's added just over 2 meters of pipe, 4 bends, and when I click OK, the loop is modelled. Here I can see in the reference CAD model the original pipe route. Here's my new expansion loop. Of course I can investigate this, see if I'm happy with it, see if there's any collisions, again having the CAD model there in the background, and I'm happy with that, so I'll just rerun the analysis. Now the analysis is complete one final time. I see the expansion case is no longer red, and if I check the results, I see the stress, the highest stress in the system, 249.9 megapascals. We've resolved the overstress issue by adding the expansion loop. Let's now take those results from Caesar 2 and take those restraint loads, and we'll take those into GT-Strudel to include as point loads in the structural analysis. So So before we review the report, we need to do one final thing. And that final thing is to switch to a Z-axis vertical to match with GT.s.r.l. Simple matter of changing the checkbox in the special execution parameters. Z is now my vertical axis. I just need to rerun the analysis one final time. So let's check the restraint summary to see what we're going to export to GT.s.r.l. Here we see in the 2000 series the restraints on the U-bolts, the largest load of which is this one here. There's 9014 at 2160 in the Z direction. So these are the loads which we will take into GT.s.r.l. To do that, on the interfaces we use the data export wizard. I'm going to export the data to a Microsoft Access database, MDB. I'll export the input data and then the required output data. So I don't need the alt sustained or the expansion case, and hit finish. I don't need all of the reports, but it doesn't hurt to export everything. It's very quick. No need to review the data. Piping analysis is done. We've made a change, we'll take that back into CADWorks afterwards, but for now we're going to move to GT.s.r.l. for the structural analysis.